Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. Hello? How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. How's this? Is that better? Because I have my mic off. 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 I'm just gonna keep there's audio. 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 Just how do we know that 5 units right? This audio. Just how do we know that 5 units right? This audio. Just there's voice in this item. There's voice in this item. If we eventually there's voice in this item. If we eventually there's voice in this item. If we eventually there's voice in this item. 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 So the kind of all of the items. So the kind of all of the items. All of the items. All the items. All the items. Then we say that files in here. Then we say that files in here would be. Then we say that files in here would be. Then we say that files in here would be. Bring 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 say that files in here would be. Oh, bring say that files. Yeah, I just picked the first item. It doesn't matter what I do. Yeah, I just picked the first item. It doesn't matter what I do. Yeah, I just picked the first item. It doesn't matter. Regardless of what I pick the first item, it doesn't matter. Regardless of what I pick, it is going to be regardless of what I pick, it is going to be regardless of what I pick, it is going to be regardless of what I pick, it is going to be regardless of what I pick, it is going to be regardless of what I pick, it is going to be regardless of what I pick.
And only keep on mic. All right.
Ah. Does this work?
I'll report. Keep going.
All right. So.
Oh yeah, that works.
All right. So. Oh, that's what. Okay. Okay. Now I understand. So.
Oh, OBS is now showing up like that though. Like reopen and close. Oh wait, no wait, just a delay.
Okay.
Okay.
So. Once we partition according to this, we can then sort each half of the partition separately, and then we can just solve from there. So in a way that this partition kind of splits our problem into halves. We have the less than 5 half, the greater than 5 half, and we should be able to sort each one individually to get our final answer. So we talked briefly about this. So given an array of items, how can you actually partition this list? Let's take a few minutes to discuss with your neighbors. Try and come up with an algorithm that can partition a list of items, given that, let's say, you want to partition according to the 6. So what algorithm can you define that successfully creates a partition? It can be any partition that gets returned. It doesn't have to be any specific one. And we want to make sure that this runs in theta n time. Let's take 2 minutes. All right, let's bring everyone back together. What do people think? Does anyone have an algorithm to partition this list? Any suggestions? Yeah?
Would you take an array of twice the size of the input array and place the, as you iterate through the entire list, keep on placing the elements. You start by placing the white element in the middle of at the end spot, and then you keep on iterating through the list.
So you start off with a list of 2 times the size. You put the item you want to pivot in the middle, and then you put the items that are smaller on the left side going this way, put the items that are bigger going this way.
Yeah, and you just have to iterate through the list once on that.
That does work, but then you end up with a lot of empty space inside the list. I'm going to want to have like the list fully packed. I don't want to add any additional spaces. Yeah?
Maybe just use Quicksort when you're comparison method based on the color and the number.
Can we use Quicksort to write a partition algorithm? Probably, except we're kind of trying to write a partitioning algorithm to write Quicksort. So yeah, it's kind of circular if you do that. Yeah?
Like, if it's red, swap it with the left.
Ooh, that's an interesting idea. You iterate through the items. If you see an item that's not red, then you swap it with an item that is red on the other side, and then you just keep doing that. That is a great idea. We will talk about that later. But yeah. Yeah.
You can keep 2 pointers, one at like 8, like the next turn, and one at 8. If it's rooted to a red item, you swap it with the start and you start by 1. If you want to swap with it.
Yeah, that. We're definitely going to be talking about that later. That is the more efficient one than the one that we're currently looking at. Your idea was effectively like what the first idea we were thinking of. The idea is you just create 2 separate arrays first, right? So you create an array for red items, you create an array for blue items. You might create an array for white items as well. And then you just look through each item, you put it in its right spot. And then once you have a list of red items, a list of white items, a list of blue items, then you just create a new array of size n, and then just put them back in. You put all the red items in, then you put the white items in, then you put the blue items in. So yeah, it's very similar to what you were thinking of. The main thing is instead of creating a single array of length 2 times n, we just create 3 arrays of length n to start with. Yeah. I can't hear you, sorry. Yeah, I think you're thinking about the same thing as what the other people said. Keep that in mind. We'll come back to that. All right, but in any case, it does seem like there are ways to partition the list in theta n time. So here's kind of the general way that Quicksort works. You start off by partitioning on the leftmost item. So we take the 32, we partition, then we quicksort the left half, and then we quicksort the right half recursively. So here is the first step. We partition these items according to whether they're less than or greater than 32. We quicksort the left half. We are not going to show exactly how this works. It's just this recursive tree. Eventually, it gets all the way down. And then we quicksort the right half. So here's kind of what the core part of the quicksort is. It's this partition algorithm. And as long as we get this to work in theta n time, then our quicksorting algorithm is going to run relatively efficiently. Now, Quicksort was named this by Tony Hoare It really should have been named partition sort, but Tony was saying, hey, it's quick. Let me call it Quicksort. And it turns out Tony was luckily correct. Quicksort is one of the fastest sorting algorithms that you'll see. So now let's ask how fast Quicksort actually is. Now we do need to do some math to figure this out. It's not as easy as a traditional like program because it does depend on how hard or how many partition operations we need. So we're going to be looking at this. Partitioning is generally going to take theta k time, where k is the number of elements that you're working with. So if you have a list of n items, it takes n time to partition it. But we can't really count how many partitions we will need because it really depends on where the pivot ends up. Let's take some look at this. So in the best case, in the ideal scenario, the pivot is always going to end up in the middle of our list, right? So we take this item, it ends up going somewhere around the middle. Why is this the best case? Anyone want to? Yeah. Yeah, even split between numbers that are less than or greater than, we're kind of splitting the problem down into two halves. And if you remember from our merge sort videos, if we do this, then we should end up getting a nice even distribution, nice smaller problems over time. So each time we do a partition step, we split this further and further. By the time we hit size 1 problems, there's no real reason to do any further sorting. Size 1 problems are effectively already sorted. A list of length 1 is fully sorted already. So what's our total time on this case? Someone said n log n over here? Yeah. Our runtime is going to be indeed n log n. If we look at why that's the case, the total work at this top layer, it's theta n, because we have n items here. The next layer, we have 2 halves that are n over 2 each. This layer, we have about 4 quarters that are n over 4 each. Each of these layers totaled up to a total amount of n work. So the total runtime is n times h, where h is this height of this tree. Now we are kind of assuming that the tree stays like the same size. Each layer still has the same number of elements. That isn't quite true, but it's close enough that we can say it is. In practice, the difference is a factor of is a value of n. Like the total number of black items here is equal to n, or theta n. So it's n log n minus n, so it ends up being n log n. So what about the worst case? In the worst case, we're going to have a lot of these like layers, as many layers as possible. And first off, what would the runtime be in this case? And second, can we come up with like an example list that might cause this behavior to occur? Let's take a minute or so to come up with these ideas.
No. I don't know far out. I don't know far out.
Definitely is not. Do I continue to screen last? I did try sewing left bit, but I don't really want this. You're kind of bad. Yeah. I still play some. Just actually really good out. All right. Let's bring everyone back. First off, what is the runtime? Anyone have a suggestion what the runtime is? Someone, yeah, in the back? Yeah, you. Yeah, n squared. Why is that? Yeah.
In the worst case, it will be each partition will just be the next element.
So you have to do the partition which takes in time, and you have to do that with each element that times it. Yeah. In the worst case, we always pick the leftmost item, and it doesn't really split the problem in half. You get n time for the first layer, n minus 1 for the second, n minus 2, and so on. That adds up to n squared. Yeah.
Why is this faster than merge sort? Because I thought merge sort would kind of do the faster.
We'll get to that. The question was, why is this faster than merge sort? Because right now it seems like I'm making a pretty good case that it is not faster than merge sort. All right. Can anyone come up with an example of an array that would actually cause this type of runtime? Yeah? Right side. This side. You.
6, 5, 4, 3, 2, 1.
6, 5, 4, 3, 2, 1. Yeah. Reverse sorted a list.
Basically, the first item is the biggest number.
Yeah, that is one way you can do this. If you have a reverse sorted list, that is going to cause this really slow runtime. Any other examples? Yeah?
It's like an already sorted list as well.
Already sorted list? Yeah. Do you have another example, or was it the same idea? Yeah. It's kind of weird. If you input to Quicksort a list that is already sorted, then it is going to take more time than if you input a completely randomly ordered list. It's kind of funny here. The best case is this n log n time, which is the same as merge sort. The worst case is n squared. Now, n squared is really, really big. It's much bigger than n log n. If you're dealing with a list of 1,000,000 items, n log n is just 1,000,000 times 20. Log n is just about 20 at that level. But if you're dealing with n squared, that turns into like 1 trillion, right? 1,000,000 squared is 1 trillion. So that's a huge difference. So why is it that Quicksort is actually fastest? Well, as it turns out, on average, if I give you a random list, it is going to end up being n log n in expectation. Now, the rigorous proof does require quite a bit of advanced math. You need some probability theory, you need some calculus, but the intuition can be easy to see. Here's one argument. Let's say that we're really, really unlucky, and we always end up 10% close to the edge. So instead of being a 50-50 split, we always get a 10-90 split. What would be the runtime if this happens? Well, let's see. We split into this 2 sections, 10% and 90%. Then we split each part into 10% each. So this is 100th, 900th, 900th, 81 over 100. The total work at each level is still theta n. So we just need to figure out how many layers we have before everything goes down to 1. How many layers do we have? Log? Yeah, I think it's log 10 over 9 of x, right? Because 10 over 9 is the inverse of the factor that we're reducing by. And if you remember, all the logs are actually just the same thing times a constant. So that means that it's just still log x. If the height is log 10 over 9n, that's just O of log n. So we still end up at O of n log n, even if we are super unlucky and we always get an item that's 10% away from the edge. So even in this really unlucky case, we still get n log n time. Now, another explanation is that Quicksort is actually just a binary search tree in disguise. If you look at what's going on, right? We take the 5, we insert that, and then all the rest of the items are just putting into like the left and the right side according to BST sort. And if you remember, binary search trees, they generally do take a lot of, they can potentially take n squared total time, or they can have like height that is theta n. But it's not very common to have height theta n tree unless you get really unlucky, right? Most trees are going to be bushy and they're going to have log n total height. Whereas you are going to get a very few spindly trees, but the probability of that is extremely low. That is assuming you do a random insertion operations. Now, if you do some empirical tests, you can show that this is actually the case. Here's what happens if you do 10,000 lists with n equals 1,000 items. And it turns out the mean is just about 2n natural log n. The standard deviation is this value, which is just about 0.648n. In practice, that means that you are going to get close to n log n, regardless of what list you pick, as long as it is a randomly generated list. So basically, like, you are never going to get items that take like a million operations to get a quicksort complete if you have a list of 1,000. So here, at least, we can see that it is the same as merge sort, at least. A randomly chosen array case is going to end up being n log n, the same as merge sort. So at this point, the only difference is the constant factor. Remember that theta bounds, they ignore constant factors. So we still don't really know which is going to be faster. It all depends on which one has a better constant factor. So why is this quicksort better? Well, we can't really say from this theoretical analysis yet. So we are going to actually have to run some code to figure it out. So we'll look at how that actually works in a bit. But first off, here is just a quick statement about all of the algorithms that we have so far. Heap sort was our n log n runtime, but it's really bad with caching, so we're not going to use that. Insertion sort is really fast if you have an almost sorted or small array, but normally it's theta n squared, so it's slow. Merge sort is our theta n log n. It's guaranteed n log n, so it's nice that way. Quicksort is actually slightly faster than merge sort by constant factor, but it is going to take n log n in expected time, not in guaranteed time. Now, here's just a quick historical aside. As it turns out, remember that problem that Tony Hoare was trying to solve, where he was having a list of words and wanted to sort it? As it turns out, Quicksort was the completely wrong tool for this job. The language that Tony was using didn't support recursion, so you couldn't really do a quicksort effectively. And sentences are generally shorter than 15 words, right? Most sentences are not that long, so insertion sort is actually going to end up being faster than quicksort in those cases. Josh actually emailed Tony Hoare a while back, apparently in 2013. Apparently, he was entirely right. Tony made a mistake, tried something out, accidentally came upon the best sorting algorithm in existence, and it turns out not to have worked well for him. This kind of thing happens, right? History is all about randomly coming up with something, leaving something out to dry, and oopsie, you've discovered penicillin. Yeah, same thing happens with quicksort. Now, let's take a look at how we can potentially avoid these worst case behaviors. So, in average, we are going to get n log n runtimes, but n squared does happen occasionally. In particular, the occasions where n squared happen, they actually happen fairly commonly, right? If I just pick a randomly sorted array, then that's not likely to have an n squared runtime. But real modern data sets aren't actually random, right? They are going to have some structure to them. So if, for example, I send in a list that's already sorted, that's going to be really slow for our quicksort. And can you imagine a case where I accidentally try to resort something that I've already sorted once, and that causes this quicksort behavior to get really slow? Yeah, I can imagine that someone accidentally resorts a list by mistake, or maybe the list is mostly sorted to start with. They just added a few new items that they want to resort. In any case, it seems like quicksort might potentially cause these issues. And in reality, we are going to end up having these almost sorted lists sent in as input. Another example that wasn't covered, that no one came up with so far, is an array with every single item the same. If you look at the three-part partitioning, and you only allow one pivot item, then an array with all duplicates is going to actually end up causing the same n squared runtime. So we're going to need to try to figure out ways to avoid these worst case behaviors. So let's try and come up with some ways. Here are some quick philosophies. One way is you can add some randomness to the approach. Maybe you, instead of picking always the leftmost item, you pick a random item in the middle. Maybe that'll help. You could also try adding randomness in other ways, maybe shuffling. Another approach, maybe we want to pick the median, right? If we pick an item that's within the middle 80% of our list, then we've already seen that that guarantees n log n runtime. So is it possible to find the median precisely? We could also just try to think about it a bit more, like look at it at a metastate, switch to another sorting algorithm if we start realizing, hey, this is taking a long time. We could also do something to the array earlier, like pre-process things, see if there's any information we could glean from the array first before we actually do our array operations. Let's take a look at each one. The first approach is to just add some randomness to the list. If the pivot is effectively a random item, then we are going to get n log n. But those rare n-squared cases do happen because your array is already sorted or the array has all duplicates. So if we're just working with bad orderings, we can fix this by just picking pivots randomly, right? Instead of always picking the leftmost item, we can always pick, let's say, an item randomly in the middle. That way, even if the array is already in sorted order, we should end up getting approximately half splits. Another good way is to kind of shuffle the list first. It's kind of weird that in Quicksort, the more sorted your list is, the worse Quicksort gets. But because of that, it ends up being that the best way to Quicksort something is to first shuffle it entirely. We discussed last time that you can shuffle an array in theta n time using the shuffling algorithm we discussed. So that just adds a theta n time step at the start, and it does mean that we managed to get n log n runtime practically guaranteed. Now, the second strategy does require care to avoid the n-squared behavior on an array of duplicates. We will talk about this a bit. As it turns out, there was a common bug, even in well-known textbooks, related to this. But it does seem like this does work. Now, you might be saying, if I take a list and I shuffle it, it's just as likely to reach a sorted order than it is to unsort a list, right? Like, there's a chance that the shuffle is going to end up giving me back a sorted list. But that's very unlikely, right? If I pick a random list that's randomly ordered, it's unlikely that it gets shuffled back into a sorted list, right? If I take a deck of cards, I'm not going to shuffle it into its original state. The main reason why we do this is because, generally speaking, data tends to come pre-shuffled, or pre-sorted, sorry. It is more likely that I get a sorted order to start with than any particular random order that you start with. Now, another approach, we could try to pick this pivot better. As it turns out, it is actually impossible to do this. You can prove mathematically that if you have a pivot selection method that is both deterministic and constant time, then Quicksort is not going to be able to run in n log n time guaranteed. Regardless of what your pivot selection method is, you cannot guarantee n log n. There's always some way for me to find an input that causes worse runtime. McElroy has an actual algorithm to do this. Given a quick sorting algorithm and a pivot selection algorithm, find a way to pick a list such that it causes n-squared runtime. But in effect, if you want an n log n runtime, you need to include some randomness, and you need that possibility that mistakes might occur and you end up sorting a sorted list. Now, I did say constant time here, because in theory, you could just find the median item. The thing is, finding the median item exactly, that does take a bit of time. You can come up with the median in theta n time, and if you do that, you do get worst case n log n time. But as it turns out, it is going to be slower than merge sort. We're going to come back to this in a bit about how you actually compute the median. For now, keep that in the back of your head. We are eventually going to talk about this. Now, the third approach, introspection, like we can just watch when our recursion depth goes too far, right? Imagine we have a list of 1,000 items. We might say we expect at most 10 layers of recursion. So if we get more than 20 or 30 layers, that feels like it might be a bad list. Let's just try a different approach if we hit 30 layers of recursion. And this works. It's perfectly reasonable. Not particularly common in practice, because you do kind of do a bit of work and then you realize, oh, I might not want to be continuing to do Quicksort. Let's switch to something else. So it does add a bit of extra time there. Overall, it's also a bit complicated to code. Like, how do you determine that your recursion depth hits 30? It's not easy to tell without like a lot of like auxiliary variables in your code. So overall, it does seem like right now our best bet for Quicksort does incorporate some level of randomness. So I did say that Quicksort is the fastest. Actually, before we get on, are there any questions up to here? All right. Now, I did say Quicksort is the fastest, right? But this is only really true if we pick our pivots in the partitioning algorithm correctly, and how we deal with the worst case. So let me just try running a speed test on this. Here I have some Python code. I have a bunch of code that runs Quicksort in various different ways. And what I'm going to do is I'm going to just test it out. Here are 3 different sorting algorithms that I have. The first one is power sort. It's actually the built-in Python sorting algorithm. And it is going to beat all of our sorting algorithms today. Kind of the reason why is because Python actually uses a faster system than what we have access to. Python itself is a really slow language normally. So what Python sorting algorithm does is it actually just runs a C program under the hood. And C is automatically 1,000 times faster. It's going to beat us. And also power sort is designed way, way more efficiently than anything we're talking about. It's way more complex. Merge sort is just the standard merge sorting algorithm that we've come up with. Quicksort L3S is this 3-pass sorting algorithm where we split into small items, even items, and big items. And right now, I'm currently setting it up so that it is going to try to shuffle the list. So let's take a look. Here I'm going to generate 10,000 different arrays, all with 1,000 items each, with a random sequence on each item. And I'm going to just run this code, see how long it takes to run each one. So let me just run this. Is this large enough for you to see? Let me
Back
just
to the room. What do you think?
Yeah, looks good. All right. Let's run this code and try to think how much time this is going to take. What do you think? All right. It's creating our arrays. Too small. All right. So power sort takes 1.29 seconds to sort this on my computer. Meanwhile, here merge sort is taking a while, but this is expected. Power sort is using C. Python is much slower than C, so it is going to be a bit slower. And power sort is also way more complicated algorithm. Has a lot more happening under the hood. And this takes me 29 seconds to solve all of these. Let's look at Quicksort. I did say it's faster, but hang on. Something weird's going on, right? If you look at this, the expected amount of time left looks like 30-something seconds. We're already at 10 seconds, so this looks like it might take a total of 40 seconds-ish. You can also see here, this one was able to solve 338 lists per second, whereas this one seems like it's around 200 to 260. So what gives? I said that Quicksort was faster, but it's not looking like Quicksort's faster here, right? Well, the reason why we're having this issue is that our sorting algorithm, because it relies so much on that constant factor, every constant factor operation that we add is going to add more time. And when we split things up into 3 separate arrays, that actually takes a lot of time. It takes time to generate new arrays. It takes time to move items out of arrays and then move them back into arrays. If we want to make our Quicksort faster, we need to find a way to do this in place. And as it turns out, it is possible to do this. So here is Tony Hoare's idea. And it is the idea that I think 3 of you came up with. The idea is you have 2 pointers, and you start them off on the left side and the right side. The left pointer is going to love the small items. The right pointer is going to love the big items. and they'll just move in, keeping all the items that they like. And when they both come to things that are they don't like, then we'll swap them over, and then we'll keep moving. That way, only items that need to swap get moved around, and we minimize the total amount of work we actually need to do with our partitioning. If we use this, then we do get a very fast quicksort. Now, we have found faster schemes since then, and the overall runtime is still going to depend on your pivot. But for now, if we just use this particular partitioning scheme, we are going to get better results. Let's take a look at how this works in practice. So here's our list. We are saying that 17 is our pivot. So we're going to start L at the left side right after our pivot. And then we start G at the right side at the very end. And what we'll do is we'll look at each pointer. Now L likes small items. So it is going to say 15, that's a small item, right? L likes 15, so it's going to move on. On the other hand, L doesn't like 19 because it is a big item. So L's going to say, I don't like 19. I'm going to stay here and wait. G, on the other hand, G looks at items and doesn't like white or blue items. It only likes red items. So L and G both are on things that they don't like. So they are going to swap them. And then we just move both in the middle to continue. Now L looks around. Does L like this item? No. L doesn't like this. Does G like this item? No. So what do? Swap. All right. And then we move the pointers in. How about now? Does L like its item? Yeah, L likes it. So we'll move the L pointer in. Does L like the next item? No, L doesn't like this. 26 is, L doesn't like 26. What about G? Does G like its item? Yeah, G likes it. It's fine. How about 26? Yeah, G likes it. It's fine. 26 is a large item. How about now? Does G like this item? No, but it also passed L already. So that means that we're basically done. We've managed to move the L and G so that they go past each other. And if you look at it right now, it does look like all of the small items or equal items are to the left, and all of the big items are to the right. We've successfully partitioned this list. So the last thing we need to do is we need to just move the pivot into its right spot. So we'll swap 2 with 17. And we do end up getting this list where all the blue items are left of the pivot, all the red items are right of the pivot. Seems like this works. Does this work guaranteed? Can someone come up with a good argument as to why this always works? Anyone? Yeah.
I mean, kind of, if they both stop before they cross, you have a smaller item on the right of the bigger item. That couldn't be if you're having a two explain. We have to swap them. And if they cross, like the C behind challenge, the C behind G already make up the whole list. So you already have like the smaller ones on the left.
Yeah, that's a good reasoning. If you look at this state, right, regardless of how L and G are, because we always swap them, every item before L and every item after G are things that L and G like respectively. L likes all the items that it looked at. G likes all the items that it has passed it. So that means that all the items that are before L, they must be less than or equal to the pivot. And everything that's after G, it must be greater than the pivot. When they cross, that means that all items have been sorted into their appropriate bins, either the small side or the big side. So if we do this, then the partitioning scheme should work. Now, what do you think the runtime is of this? Let's take a look. Here I have Tony Hoare's approach. And just for time purpose, I'm going to reduce this to 5,000 arrays. Let's see how this runs. So the sorting algorithms, power sort is still going to be way faster. It finishes this in 1.05 seconds. Merge sort goes through everything. Well, it took 30 seconds to get the 10,000 set, so this is probably going to take around 15 seconds. Let's see. Merge sort takes 12 seconds. Quicksort with this 4 partitioning takes 5 seconds. It's a big difference, right? Just because we switched to using the 4 partitioning algorithm, we end up getting this much faster runtime. So that's why Quicksort ends up being faster than merge sort in practice. We can't really prove this theoretically because it does depend on these constant factors, and that will depend on your computer. Like if you ran the code that I ran on your computer, you're probably going to get different numbers. My computer's probably not the same speed as yours. But generally speaking, Quicksort using Tony Hoare's partitioning scheme is going to end up being faster than merge sort. Now, before we finish off, I want to end up discussing that median idea, right? If we don't want to use randomness, like we could potentially compute the median exactly. And if we're able to do that efficiently, then we should be able to get this to work, right? If we can get our median, then we can guarantee n log n runtimes. So let's try and figure it out. How do we compute the median? Let's take a minute to just come up with a very simple median solving approach. If you can get your algorithm to run in linear time, that's a plus, but the linear time median sorting algorithm is actually really hard to find. So if you can get an n log n runtime median sorting algorithm, that's fine. Anyone want to come up with an idea? Let's take a minute to discuss it and I'll bring everyone back.
Thing where you like send a note to this left server and look at what reads and correctly. People are discussing these context and understanding. That's you're saying something speed. I'm not as much I just play a lot of the bombs.
All right. Just for the interest of time, let's bring everyone back. All right. What do people think? Does anyone have an n log n time algorithm to find the median of a list? It can be any. It can be silly. Yes. Step 1: merge sort the list. Step 2: take the middle item. That finds the median. Is that a good idea? Do we want to use this as our pivot finding algorithm to partition a list in order to sort it? Not really, because it seems like we're sorting the list to figure out how to sort the list. So this is not a good idea. We definitely don't want to just sort the list first. And if we did try this, it is going to be really, really slow. Now, if we were able to compute the exact median in theta n time, that would be really great for picking an item for partitioning. It would create a safe quick sorting algorithm. You can actually use partitioning to find the exact median. This is known as the best known median identification algorithm. Now, this is also a somewhat randomized algorithm. So you do kind of need to worry about this. But here's kind of how the partitioning algorithm works. In order to find the median, we first partition the list. And then we look at this. After we partition, which side is our median going to be in? Is it going to be on the left side or the right side of 9? The right side. Why do we know it's on the right side of 9? Yeah, because the larger side had more than half the items. So what we'll do is we'll only look at the right side, and then we'll look at this. The pivot now lands here. Which side will the median be on? Left side or right side? Left side. Why? Yeah, because the middle item here, it should be on the left of this pivot. And then if we keep doing this, then we do end up getting the median eventually. Now, how much time does this take? Well, if we assume that we have a really worst case list, then it still takes n squared time because the pivot keeps moving one space. But on average, you are going to have the problem each time. So you end up getting 1 plus 2 plus 4 plus 8 plus up to n, which takes theta n time. So on average, this is a theta n pivot taking algorithm. here's kind of like a brief like mathy or like a intuitive diagram as to what I just said. On average, the pivot is going to end up halfway there, and if we assume that, then it does take theta n time. Now, that does rely on like random chance, though. So what if we wanted to find the median and guaranteed theta n time? As it turns out, that is possible, and this paper from 1972 talks about this. This is called the PICS algorithm. It was developed in 1972. It's not really used too much. As it turns out, this paper is written by a bunch of people whose names you're going to become very familiar with. Rivest is the guy who invented RSA. He's the guy whose name is Rivest Sherman Alkahest. Bloom, Floyd, and Tarjan were all Turing Award winners, which is kind of like the Nobel Prize for computer science. And von Pratt was just there. Sorry. So let's actually see how this works. I took this algorithm, and I actually coded it up in Python. And if I look here, I have the exact median approach that I said was slow, and I have the PICS median approach as well. And I want you to think, which one do you think is going to be fastest? How many people think Quicksort L3S is going to be fastest amongst our Quicksort options? How many people think Quicksort 4 is going to be fastest? How many people think exact median? How about pick median? All right, everyone's betting on pick median. Let's see how this runs. Save. All right, first off, we're going to have our power sort, and power sort's going to beat everything because it is in C. So it is going to win. And let's run it. Power sort gets it in less than 1 second this time. Merge sort is going to be our baseline for our nlog Python code. And if we see this is going to take just about 15 seconds, let's see. Come on. And this takes 17 seconds. Now our Quicksort L3S, we already said this is going to be slower than our merge sort. So this is probably going to take around 20 seconds. Let's see how this runs. 3,000, 35. "20 seconds. Now the whole partitioning one we said is really fast, and as it turns out, it's beating merge sort by a factor of 3. It's 5.33 seconds. The exact median, it doesn't look too bad actually. It looks like it's taking just about the same as L3S, or close to. And it finishes in 15 seconds. And here is PICS algorithm. It is slow. It is still running, but it looks already like it's going to take about like 40, 50 seconds to finish. The bottom line is, if you want a Quicksort that's fast, you need to have randomness involved. Now I'm just going to let this finish running. That's kind of all I have for today's lecture. But yeah. It's, I'm running it over. Yeah. Okay, for those of you who are got paste pen for Celeste, I'm a lecturer of computer science. Our normal Zoom streaming system is broken today, so I was just using my Twitch channel to teach class, and for some reason someone decided to paste ping. Sorry. I assure you, I still play Celeste. It's just, I don't actually speedrun the game, I just play mods. Sorry for this.